Okay, so welcome back to another video. So in today's video we are giving the limit as n approaches infinity of the n square root of 1 factorial times 2 factorial times 3 factorial all the way up to times n factorial divided by the square root of n. So we are given radicals, one with the numerator as n squared and the denominator is just square root, but we're also given factorials within the n square root. So this might be a little complex looking, but hopefully if we do some manipulations rewriting our limit, then things should just come out nice. Let me just define this. Let me just define what our function, rather, in terms of n as I. So I'm not going to write the limit to the side, so I'll just define I, which is equal to this, the limit here, excluding the limit, I mean. So n squared, and then 1 factorial times 2 factorial times 3 factorial, all the way up to n factorial. Okay, and then we divide, and then that's divided by the square root of n. Okay, and let's take the natural log of both sides so that we get ln of I is equal to the natural log of the same thing above. Right, so n factorial, and then that's divided by the square root of n. But now notice that on this the right hand side, I can rewrite this using our using the rules of natural logs. So this means this will be ln of 1 factorial times 2 factorial, and then we multiply this all the way up to n factorial, and then we take the 1 over n squared, that's its exponent, and then we subtract with so this will be minus the natural log of n to the power 1/2. So simply we wrote it with using our rules of natural logs, so we have a difference. Okay, so now again using rules of natural logs, I've moved the exponent to the front of our natural logs. So I have, this will be 1 over n squared, and then this is multiplied by okay, and then I can expand this, and I can expand the factorials out, but not only that, I'm also continuing to use the rules of natural logs. So we have our inputs in terms of products. That means we can actually use the sums of natural logs. So then this will be ln of 1, and then plus, let me actually write this in parentheses. We're going to group these. So, okay, so ln of 2 times 1, so that means this will be ln of 1 plus ln of 2. Okay, and then plus ln of 3. Well, okay, well, you get the gist, but I'm just gonna skip that and then go to the last term. So then we have, let's see, the natural log of 1 plus the natural log of 2 plus dot 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 plus all the way up to the natural log of n. And then I'm gonna subtract that with 1/2 divided by, multiplied by ln of n. Simply just using rules of natural logs, I move the 1/2 to the front of the natural log. Okay, so now the next step here is taking a look at the inside bracket when we're taking the sums. This means I can actually rewrite the expression differently. So let's see, going back, so 1 over n squared. So this time I'll rewrite, so we have ln of 1, 1, 2, all the way up to n times. So this is n times the natural log of 1. And then we have ln of 2 all the way up. So it decreases by 1 from each of the sequence. So when we start with 1, we go to 2, but then the number of the natural logs of those numbers specifically decreases by 1. So this time we have plus n minus 1 of ln of 2. Okay, and then now next decrease by 1 again, so n minus 2 of ln of 3. Okay, and then plus dot dot dot, and then we only have just one term for ln of n, so this is just ln of n. Okay, and then subtract that with 1/2 multiplied by ln of n. Now the next step is taking a look at just our inside expression. What I'm going to do is I'm actually going to add a 0 into the inside expression. So what I'll do is I'll so let's start with the beginning. So ln of natural log of 1. What I'll do is I'll actually add and subtract a n times ln of n, okay. And then the next one, our next term is plus n minus 1 times the natural log of 2, okay. And then I'll add and subtract a n minus 1 multiplied by ln of n, and then plus okay, same thing, ln of n, okay. I'm just gonna move to the next line here. So then we have next plus so our next one is n minus 2 ln of 3, and then I'm going to add and subtract n minus 2 and then times ln of n to ln of n, and then moving on so far so forth. So you see the pattern of what we're doing here. And then we have ln of n, and then actually I'm actually going to add and subtract an ln of n again. Here, I'll put this in parentheses so we know where it starts and ends. So this is specifically manipulating the inside argument. Okay, and now from here, now I can actually just use our rules of natural logs. What I'll do is I'm actually going to take the first two terms that corresponds with. So we have an n times ln of 1 minus ln of n. I'll take those two corresponding terms together and then do the same thing with the next pattern. So n minus 1 ln of 2, and then with n minus 1 ln of n, n minus 2 ln of 3, n minus 2 ln of n, n minus 3 ln of 4, n minus 3 ln of and you see the pattern, so on and so forth. We're going to take those two terms and then use the rules of natural logs to manipulate some stuff. So then we have so natural log of n, and then divide by 1 over n, and then add this with n minus 1 to the natural log of, let's see, so this will be 2 divided by n, and then next would be n minus 2 of multiplied with ln of 3 divided by n, okay, and then we add this with the natural log of n divided by n. And now the last step is, now you'll notice that we have a plus n times ln of n, then a n minus 1, and then plus n minus 1 ln of n plus n minus 2 ln of n, and then all the positives. So you'll notice that that's actually, we're taking the sums of the decreasing numbers starting with n, and then we subtract by 1 each time. So with that formula, it actually comes down to, it's a special formula, so it's actually equal to n times n plus 1 divided by 2, and then multiply with the terms of ln of n. So here I could actually justify by saying it this way. And I literally forgot the name of the name of this formula, but this is definitely something you guys have definitely seen before. So let me put this star over here. And then this is star supposed to generate that. So it's n. I'm just going to ignore the term n plus 1, ln of n for now, but you'll see what the scalar multiply with that. So you'll see what the pattern's doing over here. So we have n, and then plus n minus 1 plus n minus 2 plus n minus 3, okay, so on and so forth. You'll notice that we're actually taking the sum of our partial sum from k is equal to 1 to n of k, and so that formula actually recursively gives us n times n plus 1 divided by 2, and that's what justifies the star over here. And so what I'll do is, okay, so this is our inside expression. So coming back from here, we have a 1 over n squared. So I'll distribute everything 1 over n squared into all our terms here. And I'm also going to skip a step and factor out a 1 over n as well. So that means I have a 1 over n, then that's being multiplied with, okay, so we have n divided by n multiplied by ln of 1 divided by n, okay, and then plus n minus 1 divided by n of ln of 2 divided by n, and then just skip the 3. You just keep going forward with the sequence, so, or the series. So 1 over n, and then ln of n divided by n, and then I'll distribute the let's see, the 1 times, or 1 divided by n squared over to the n times n plus 1 divided by 2. And so what that gives us, this will be plus n plus 1, and then divided by 2n, and then multiply with ln of n, and then going back to subtract with minus 1/2 ln of n. And now I actually do this, why I factor out a 1 over n from here after just distributing the 1 over n square, is that the the input expression actually forms a nice little partial sum. So what that sum comes down to is it's actually can be written as, so let's see, so this is n, k is equal to 1. So now the partial sum is expressed as follows. So this is n multiply or minus k minus 1, that's the quantity, and then divided by n, then multiply with ln of k divided by n, and then plus the natural log of n divided by 2n. That comes from, so I guess I can really just show the work here if I really need to. So just ignoring the ln of n with that factor, let's just focus on just the scalars n plus 1 divided by 2n and then minus 1/2. So let's see, n plus 1, 2n, minus 1/2. Let's see, I get a common denominator, so let's see, 1 plus 2n, then minus 2n, n, and then therefore this is just 1 divided by 2n. And then we just multiplied the natural log of n over here. So that's what we got. Before I go any further, now what we can do from here, specifically with the this input over here, we can actually write this as a form of a Riemann sum. So let's see, right? Riemann sum. So this means when I'm writing it as a Riemann sum, that means I'm going to have to take the limit as n approaches infinity. So let's see, we have going here, the limit as n approaches infinity of, so this will be, let's see that, yeah, that's just 1 over n, and then times our partial sum series, k is equal to 1 of n minus k minus 1 divided by n multiplied by ln of k divided by n. That means this can be rewritten as a Riemann integral. So this is the integral, specifically it goes from 0 to 1 of 1 minus x, and then that's multiplied by ln of x dx. Okay, and from here, it's not that difficult to show that we will need to do some integration using integration by parts. So I'm going to let u equals ln of x, du is equal to 1 over x dx, then dv is equal to 1 minus x, put in parentheses, that's the quantity dx, then v is equal to just x minus 1/2 multiplied with x squared. And so we combine our use our integration by parts, u times v, subtract with the integral of v times du. So let's see, I get x ln of x, then minus 1/2 x squared times ln of x. And okay, let me just write this as we're evaluate this from 0 to 1. Okay, and now we just multiply our v du. So let's see, subtract with the integral from 0 to 1 of, let's see, so this is x minus half x squared, and multiply with 1 over x dx. Let's just evaluate this integral first before we continue any further. Okay, so now when I distribute the 1 over x into here, that means this integral, we're going to get 0 from 1. We're going to get that this is 1, and then subtract that with 1/2 x dx. And now just take the definite, evaluate the definite integral. This is just x, and then minus 1 over 4 x squared. Now just put everything back together. So let's see, x times ln of x minus 1/2 x squared ln of x. Yeah, okay, and then subtract x, and then distribute the negative, so we have a positive 1 over 4 x squared, and then evaluate this from 0 to 1. So now if I plug 1, so let's see, for x equals 1, let's see, ln of 1 is just 0. So 0, 0 here, and then I have minus 1 plus, let's see, 1 squared is just 1, so minus 1 plus 1 over 4 is negative 3 over 4, okay? And if I put 0, so let's see, 0, 0, 0, 0, so minus 0, so therefore this is equal to negative 3 over 4. Okay, so therefore, I just put the triple dots, but that's not our final answer. Therefore, the limit as n approaches infinity of 1 over n, and then of our partial sum of n minus k minus 1 divided by n, then multiply with ln of k divided by n, which is simply equal to the integral from 0 to 1 of 1 minus x ln of x dx is equal to negative 3 divided by 4. And let me emphasize that by drawing, or not really drawing, but underlining our limit in black. We found that term. Now we have to find what ln of n divided by 2n equals to. So let's see, we'll take the limit of that. Okay, the limit as ln of n divided by 2n. You'll notice that if I plug infinity, we get an infinity over infinity indeterminate form. So therefore, using L'Hopital's rule, then I'll take the derivative of the top. That means ln of n is just 1 over n, and then that's divided by 2. So this means if I plug infinity for n, that means 1 over infinity is just 0. So that means we get that this is just 0. Okay? Therefore, we come to the conclusion that the natural log of the n square root of 1 factorial times 2 factorial times 3 factorial all the way up to n factorial, and then we divide this by the square root of n, that's equal to negative 3 divided by 4. Okay, but we're not done yet, since we've shown that this is equal to negative 3 over 4, which is still set equal to the natural log of I, where we want to find what I is equal to. So then I'll just take the e base to both sides, so e ln of I, and equal to e negative 3 over 4. So therefore the conclusion is I is equal to e to the negative 3 over 4, like so, drawn in this black box. Now I know I said I is equal to the this whole function over here in terms of n, but then we take the limit, so it comes down to that. So when we take the limit for this, we get that this is equal to e to the power negative 3 over 4. All right, hope that clarifies stuff. Okay, it's pretty cool if you ask me.